In this tutorial, I just want to discuss the pocket belt feature in Sidewinder. So I've went ahead and just opened a new file. So the easy profile is really a slick way to work with pocket belt conveyors in Sidewinder. I can go ahead and I'll just put in some geometry here. I'll say we go over 5 meters for a loading point, maybe up 15 meters, and then go over 5 more meters. So there's our profile. Generally with pocket belt conveyors, unlike a regular typical conveyor where you don't have a one-to-one scale or you have a much longer conveyor than the elevation profile, pocket belt conveyors are typically more one-to-one. So if we right-click here and we just say one-to-one aspect ratio, you'll see it shows us the true one-to-one ratio of the conveyor. Also, unlike a conventional conveyor, usually with pocket belt conveyors, obviously, especially if they're straight vertical, they've got these inflection pulleys here. So you can go ahead and manually add those in the vertical profile, but we've actually made it really easy for the end user. If you go over to the material input, or the main page here, and we just simply change from a trough conveyor to a pocket belt conveyor, as soon as I change that, you'll see we get some new tabs over here. One of them is the Sidewall tab, which is we're gonna discuss that in a minute. But also if I go back to my geometry here, and I'll just manually update, you'll see that it automatically adds these pulleys for us. So that's pretty slick. Regardless of what we put in for our geometry here, we can go ahead and pretty easily, pretty quickly lay out our conveyor just using the easy profile really, really quickly. So again, we just go to our main page, switch to a pocket belt conveyor, come back, and there we go. We'll also notice that if I go into the vertical profile here, like this first pulley type, it sets each of these as different pulley types. So the first one is an inflection pulley. Obviously the belt would be bending up with pocket belt, so it's a special type of pulley. So it puts that as a pulley type 3. This is a normal bend pulley, puts that as 2. As typical or as usual, our drives are always type 1s. Again, on the return side, this would be an inflection pulley, another normal bend pulley, and our tail pulley. So you could go ahead and change these if you want to make the tail pulley a type 4 or whatever. You could go ahead and change that as you like, but by default it automatically puts those in, which is pretty slick. The only other thing that's, I guess, a little unique on the pocket belt conveyors, when it does create them in the vertical profile, you notice it doesn't use the return side mapping element like we do with regular conveyors or longer conveyors, simply for the fact that it's just easier to work with, because normally you've got these special pulleys in here and whatnot. So it's easier just to actually work with each of the elements as they are. Normally your pocket type belt conveyors are not super complex, so it's just as easy to work with them in here. Of course, all of this information still works out just fine if say we had a long head and we were going to put a drive and a take up at the head and just a regular tail pulley, just like we normally do with a regular conventional easy profile. We can just click on those layouts and add those in there. Super simple. I'm just going to go back to a take up at the tail and my head drive just for now, and we'll just go back to, say, maybe 5 meters. Let's go up, let's maybe just go up 10 meters for now, so that gives us, what, about a 34 degree slope. So that's pretty much it for working with the geometry. One other note, the adjust to end, this is a useful tool. Say this was our conveyor and we actually looked at it and said, well, this pulley really only goes back maybe 2 meters, and then here, for whatever reason, our conveyor only went back minus maybe like 12 meters. Like I said, maybe there's something with your structure or whatever that you're doing, something's different here. This adjust to end is always a really slick feature. You just go to this whichever element you want, either that one or this one, whichever one you want. In fact, I could combine these two if I want and just make them one. But I just click on that element, say adjust to end, and boop, it automatically just ends wherever we need to. So that's really slick. Clearly, if I was at minus 12, I could come over here and just say, oh, adjust to end, and it just brings that right back to where it is. So if you do manually have to work with stuff, that adjust to end button is really quite slick. But again, we'll just use our default one from now, or the easy profile for now. So we go into our main input. Again, when we selected pocket belt, it's going to give us some new sidewall options here, which we're going to discuss in a minute. But let's go ahead and just put in some properties. Let's say we're going to design 125 tons per hour of limestone, and let's maybe use a 100 millimeter lump. So we went ahead and entered that, and as soon as I hit run, just like normal, Sidewinder will go ahead and auto-select a belt and belt speed and select a lot of stuff for us automatically, which is pretty slick. In this case, it's selected a 650 millimeter wide belt running at 1.1 meters per second. So there's kind of some different default rules of thumb that are built into it. One of them, the width has to be at least 3 times the lump size. It will look at the slope of the belt and what that loading is vertically, and select the belt width and the speed and whatnot to keep that vertical loading within acceptable limits as well. We'll get to that in a minute. Let's go through the inputs. The sidewall height, pretty self-explanatory, simply the height of the sidewall measured from the top of the belt to the top of the sidewall. The free edge gap is simply this free edge distance right here. So it's just from the outside of the sidewall to the edge of the belt. That's important. Again, if I go over to my frame here and look at my picture, I can zoom in wherever I want, but if I zoom all the way in, that free edge is important because that's where you've generally got your little 2 idlers supporting the belt on the return side. The next is the sidewall thickness. That's, again, pretty self-explanatory. It's just the thickness of our sidewall. So therefore, our pocket opening width is just our belt width minus 2 times the free edge distance minus 2 times the sidewall distance. And if I click on my tool tip right there, it says that pocket width is the belt width minus 2 times the edge distance minus 2 times this thickness. Our sidewall weight, this is essentially just the weight of the sidewall. This is the weight of one sidewall only, so it's just the linear weight for one side. It's put in per one side because that's generally what you see in a catalog. In the manufacturer catalogs, they just list that. We will do this in a minute, but if I actually right-click anywhere I want in here, I can select from the built-in catalogs, and if I pick one of these sidewalls, it will actually fill all this in, but for now let's just leave it blank. Minimum drive pulley, typically 3 times the sidewall height, or based off of what the belt construction is. So Sidewinder looks at both. It looks at what the pulley diameter needs to be for whatever ends up being the selected belt and rating and number of plies, but then it also looks at the other rule is that it's got to be at least 3 times the sidewall height. The inflection pulleys, those are varies quite a bit from manufacturer to manufacturer, but typically it's anywhere from 3.5 to 4 times the sidewall height is what they typically recommend for an inflection pulley. And by inflection pulley, we're talking about these pulleys right here that bend upwards. If I look at, and again we'll show this later, but if I look at the inflection pulleys, this is the inflection pulleys where it's bending upward and you've got the belt in between it. Cleat type. Few options here. Obviously none. If I don't have any cleats and I just have sidewalls, then it will just not put any cleats in there. T-cleat cleats, just a straight vertical cleat. C-cleat and a TC cleat. Those are the options available. And those are pretty much totally customizable. We can put in the cleat height, which is the distance from the top of the belt to the top of the cleat. The spacing of the cleats, again, pretty obvious, just what the spacing of the cleats are. The cleat weight, this is entered kilograms per meter, but not linear meter. It's the cross section. Again, that's what the catalog manufacturers list that is. So the actual belt weight is the sum of the core belt weight plus 2 times the sidewall belt weight plus the cleat weight in kilograms per meter times the pocket width times the number that you obviously have per meter. So all those added up together will give you the total belt weight. The cleat base width, that's simply this dimension from here to here. Maybe it's easier so if I just show that. I'll just change that to 50. You see that kind of shrunk there. If I make that 100, makes it a little longer. So that's just the width of that base. The cleat thickness, just the thickness of our cleat. Obviously, if I change that, make that big and fat to 50, see that just made that nice and large. The cleat base thickness, that's the thickness of the base. Again, if I make that 50, you see that's the thickness right there. And those numbers are important because Sidewinder actually properly calculates what this cross-sectional area is. For example, if I put in a cleat thickness and a base thickness of 0, that's where my material is sitting at. And if I go ahead and let's fix, I'm going to just fix some properties here. Otherwise, if we don't fix them, Sidewinder will automatically change our belt speed and our width and whatnot to come up with an acceptable design or a approximate design here. So I'm just going to fix a couple things just so we can show this here. So we see here with a cleat thickness of essentially 0, our material height is 83 millimeters. And we're at 41% of the cross-sectional loading. 41% of the cross-sectional loading is 41% loaded to the top of the cleat with the material on top of it. I'll show what that means. In fact, let's just do that right now. If I say I maybe put in 300 tons per hour here, let me go ahead and fix a couple things here. I'm just going to put in a sidewall height of 200, just so we fix everything so you can understand what we're talking about here. Let's maybe make this 310. I'm just trying to get 100% cross-sectional loading here for you to show you exactly what that means. Pretty close, 330. There we go. So 100% cross-sectional area means we are flood loaded right to the top of the cleat. It doesn't have anything to do with sidewall. Sidewall may be 240 millimeters. It doesn't have anything to do with that. It's to the top of the cleat. And of course that takes a surcharge angle. If I put in, say, a 35-degree surcharge angle here, I gotta boost this up again. Let's maybe say 350 tons per hour. Pretty close. 360. There we go. Whatever. 355, 358. Whatever. We're basically 100% means we are loaded right up to the edge of the cleat. That's what Sidewinder uses as 100% loading. So obviously if this is roughly half that, which would be what, 180, now we're at 50% loading. And of course Sidewinder takes in the volume. The reason we can put in all the cleat properties here is if we specify these cleats obviously take up volume. So if I make this cleat 25 millimeters thick, and maybe the base is 15 millimeters, once it adds that dimension, it's going to shift this material up. Right now we've got a height of 123. I run this with thicker cleat. Now it's 145. If it was even thicker, say it was 35 and 35, it's going to move it up even more, 165. So that cleat takes up volume, obviously. Clearly the number of cleats, same type of thing. Right now the spacing is 250. If the spacing happened to be half a meter, well, now it's going to drop down. It's going to be less high because we've got fewer cleats in there. So it's pretty slick. It's a really really powerful tool, and I hope you guys enjoy it. The TC length here, this is simply just the distance from the top of the cleat to where the TC arm starts bending at. Oh, sorry, did we get cleat? Oh, sorry, we missed the cleat angle. The cleat angle defaults to 30 degrees for a C-type cleat. Let me just delete this. Default is 30. You can put in whatever you want. If it was 10 degrees, you can put in 10. If it's 60 degrees, you can put in 60 degrees. For a TC cleat, that angle defaults to 45 degrees. And that's this angle right here. Again, we can put in whatever angle we want. If we want 10 degrees, I can put in 10 degrees. If I want 70 degrees, I can put in 70 degrees. But the default will be 45. This TC length, that's the distance, again, from the top of the base to right where that bends at. So if I put in 50 millimeters here, you can see that makes it very short. If I put in 150 here, obviously that's going to make it very tall. So that's all that dimension is. I think that pretty much wraps it up for inputs. Let's go ahead and delete some of these and go back to our default values here. Again, if I had right-clicked and went over and picked any specific one, like say a BFS 180, you can see it automatically fills this in straight from the catalog. Same with the TC type properties. You could go over here and pick 180, boom, goes ahead and fills that right in. As far as the outputs down here, all pretty self-explanatory. 300 by 180, that's just our pocket width by our height. The material area, again, as I said before, 100% is loaded, 100% loaded. This is just the area of this cross section right here. Likewise, this area here is the area, and we are, let's go back to our 20 degrees here. There we go. And I'm just going to delete all of this just so we can leave it. Let Sidewinder default some stuff for us. There we go. This area here, when we talk about the slope for both the material area and the area percentage, this is a really important number. So this is the area under this green line. So this green line is essentially flooded. So that angle right there is our surcharge angle of 20 degrees. I mean, clearly if we change the slope from 34 degrees, let's maybe go up 25 degrees, now it's 60 degrees. Now when we run that, there's our green line here. Again, that's a 20-degree surcharge angle. And it's saying that the area under this green line at our whatever maximum belt slope is, happens to be 59 degrees. So Sidewinder just looks at the whole carry side, picks out what the worst slope is, and it uses that one. That area is 0.0352 meters squared. That results in 91%. We are currently 91% loaded. The maximum tonnage we could do on this conveyor, in other words, flooding right up to this green line, if it was, this surcharge went perfectly flat, and we flooded it right there, would be 197 tons per hour. So that's a really useful number. Quite often you'll look over here, I mean, say we were going 200 tons per hour when we ran this, we'd say, oh, look, we're already 102%. We're flooded over this maximum profile here. So typically we'd probably will not want that much more than up, and there we go. So let's go ahead and, again, sorry, I should have just left these in here. We'll pick a sidewall 180. All right, we're at 109% loading with that. Most we can do is 138. Maybe we'll do 100 tons per hour. Or we might have to increase our belt speed or increase our belt width, where we've specified some of these. There we go. If we decrease to 100 tons per hour, now we're at 73%. So pretty self-explanatory, but very useful when you're laying out conveyors like this. The material height, again, that's just simply the height of the material depth right here, 78 millimeters. Our cleat height defaulted or picked 165 for this one. Our slope and our cleat spacing. So I think that pretty much wraps it up there. Of course, if I simply right-click, as always, I can export this to a DFX really slick. I can just right-click, I'll save that, jump over to AutoCAD here, go ahead and open it, and voila, got a nice completely dimensionally correct profile, front view as well as our side view. The two lines here, by the way, are simply the top of the material and where that material is at the edge. That's representing those two lines there. At some point we may actually add another, the green line is our flooded belt. At some point we may add the actual loading line there as well. Maybe look for that in a future release. So that's all available. Again, I guess I just quickly mentioned the pulleys. You can go ahead and look at any of our pulleys as well as our inflection pulleys. Our inflection pulleys obviously have all the correct wrap angles and therefore the correct tensions and vector tensions and shaft deflections and so on and so forth. The report, I can come over here. Let's just zoom out, make this a little prettier here. There we go. I'm just going to zoom in on this part right there. There we go. So we can adjust our layout, make it all pretty for us. If I hit export to report, your normal Sidewinder report. Clearly has the cross-sectional 2 views in it. It's got all your pocket belt conveyor informations right here, pocket width, sidewall height, cleats. It breaks down all your weights there, so there's your cleat weight per meter, cleat weight times pocket width, so that's the weight, per each cleat, how many total cleats you've got on the belt, and then what your total belt mass is, which is the core plus the sidewall plus the cleats, everything combined up. I think that pretty much sums up everything I wanted to quickly go through. Certainly if you have any questions whatsoever, feel free to drop us an email or give us a call. Very good. Thank you.